Okay, in this part of the video on acids and bases, we're going to talk about strong versus weak acids, what that means in terms of how we define them in chemistry, and then talk about the relationship between the concentration of hydrogen and the concentration of hydroxide ions mathematically. In the last video, we talked about just the balance and what makes something an acid or base. And then in the next video, we're going to talk about calculating pH and pOH based on the ion concentrations. And then in the last video, part 4, we'll talk about neutralization and titration, which are two things we do with regard to acids and bases. So first, strong acids, what we define as a strong acid. In this case, it means that a strong acid is something that completely dissociates in water, which means, in the example here, hydrochloric acid, for every unit of hydrochloric acid, of hydrogen chloride that you put into the water, you get a hydrogen and a chloride. They all break apart, every single one. So there's no difference between the number of hydrogen chloride units you put in and the number of hydrogen ions you get. And examples of strong bases are here. We've got hydrochloric acid, sulfuric acid, and hydroiodic acid. A weak acid is one that only partially dissociates. So in the example here, what we see is a reversible reaction like we've talked about in the past with equilibrium. So the hydrogen and fluoride break apart, and you get those hydrogen ions, which makes it an acid. But some of those hydrogen ions return around and bond with either the fluoride ions or the hydroxide ions that are already in the water. And so you don't get the complete effect of the hydrogen ions that you did with the strong acids like hydrochloric acid. So it's less than the complete dissociation. Now, it's also worth pointing out here that in these definitions, strong and weak are not to be confused with concentrated or dilute or safe and unsafe. Right? Weak acids, like hydrofluoric acids, are extremely dangerous. Weak doesn't mean it's not dangerous, it just means it doesn't dissociate. So it's a very technical definition that you shouldn't confuse with safe. So here are examples of strong versus weak acids. We've got hydrochloric, hydroiodic, perchloric, nitric is another very strong acid, and sulfuric acids, whereas weak acids are things like hydrofluoric, acetic, which is the ingredient in vinegar, hydrosulfuric, carbonic acid, which is in a lot of sodas, and hypochlorous acid. Okay, the same definitions apply to strong and weak bases. Okay, strong bases are the ones that dissociate completely, like sodium hydroxide. For every sodium hydroxide unit you put in the water, you get a hydroxide. So you get the full effect of adding that base to the water, and it makes it the most concentrated in terms of per unit of NaOH. You get every hydroxide out of those that you can. And the weak bases, again like the weak acids, are the ones that only partially dissociate or take part in a reversible reaction where you get some of the ions and then some of the ions turn back into the original product or the original reactant, and so you don't get the complete effect. These are just some of these strong bases, right? Sodium hydroxide, potassium hydroxide. You're looking at basically the alkali metals and a couple of the alkaline earth metals. Those are the ones that really strongly dissociate. And this value over here we're going to talk about more later when we're doing pH, because for a strong acid, when we're measuring the concentration of the ions, which is what you need to do in order to find the pH of a solution, you can assume that the concentration of the solution is equal to the concentration of the ions, whether it's an acid or a base. When it's a weak acid or a weak base, you can't do that because the number of ions that you get is not the same as the number of units that you put in. So we'll go over how you figure that out in just a little bit, but it's using the equilibrium expression that we've talked about in previous units. So we're going to talk a little bit about the relationship between hydrogen and hydroxide concentration, okay, and how we can calculate that. The equilibrium constant expression for water has a value of 1 times 10 to the negative 14th. And we find that, the equilibrium constant, from the ionization here. Right, since water is a liquid on the reactant side, we don't include that in the expression. So the expression is just the concentration of hydrogen times the concentration of hydroxide. those two values multiplied together always will equal 1 times 10 to the negative 14th. So that allows us to use one concentration to find the other. So if we know the hydrogen, we can find the hydroxide. If we know the hydroxide, we can find the hydrogen. For example, if we look at a solution with a concentration of hydrogen ions of 1.0 times 10 to the negative 5th molar, and we're going to assume that this is a strong acid. So in this problem, we're going to take advantage of the fact that we learned in the previous slide that the concentration of hydrogen times the concentration of hydroxide always has to equal 1 times 10 to the negative 14th. So given that 1 times 10 to the negative 14th in this problem equals 1.0 times 10 to the negative 5th times the hydroxide concentration, okay, because that's the hydrogen, then we just divide both sides by 1.0 times 10 to the negative 5th, and that will give us the hydroxide concentration. So that's the first part of the question. What we get is 1 times 10 to the negative 10 to the negative ninth. And just as a quick hint, if all the concentrations, if you've got 1 times 10 to the negative 14th and then you've got 1 times 10 to the anything on the other side, you can just find the difference between the exponent of the concentration you have in 14, so in this case 9, and that will be the exponent of the other concentration. So the second part of the question is this an acid, a base, or a neutral solution? Well, again, the determination of whether it's an acid or a base or neutral has to do with the balance between hydrogen and hydroxide concentration. So in this case, the question is, which is bigger, the concentration of hydrogen or the concentration of hydroxide? Well, the concentration of hydrogen was 1 times 10 to the negative 5th. The concentration of hydroxide is 1 times 10 to the negative 9th. 1 times 10 to the negative 5th is the bigger number, which means the hydrogen concentration is higher, which means this is an acid solution. What is the OH concentration of a 0.25 molar hydrogen chloride solution? So same basic idea here. We've got 1 times 10 to the negative 14th equals the concentration of hydrogen. Now, since we've seen already that hydrochloric acid is a strong acid, that means we can assume that the concentration of the solution is equal to the concentration of the hydrogen ions, because all of those HCl's are going to dissociate and give you hydrogen ions. So just like we did in the last problem, we're going to take both sides, divide by 0.25, and then what we get is that the hydrogen or hydroxide concentration is equal to 4 times 10 to the negative 14th. And if we were being asked to figure out if this was an acid or a base, well, if 0.25 is the hydrogen concentration and 4 times 10 to the negative 14th, which is a really small number, is the hydroxide, this would be an acid, okay, because the number for hydrogen is much, much bigger than the number for hydroxide. Okay, this time we're going to go the other way, and we're given KOH, and we're asked to find the hydrogen concentration. So 1 times 10 to the negative 14th equals the hydrogen concentration, which is what we're trying to find, times, since it's KOH, which is a strong base, and you can assume it's a strong base unless there's an indication that it's not, if it says a weak base or there's other things that will give you that hint. But if it just gives you the concentration, assume it's a strong acid or a strong base. So we've got 1.3 times 10 to the negative 2 as the concentration. So we divide both sides out, and we end up with 7.69 times 10 to the negative 13th equals the hydrogen concentration. So which is bigger? Well, in this case, it's the OH concentration, the 1.3 times 10 to the negative 2, that's bigger, which is bigger than the hydrogen concentration, so this would be a base. Again, that wasn't actually asked, but just so you get in the habit of doing that. So that's it for strong versus weak acids and bases, as well as the relationship between hydrogen and hydroxide concentrations and the equilibrium constant of water. In the next video, we're going to talk about pH, which is hinted at up here, and how we relate the concentrations of the hydrogen and hydroxides to pH, and also another scale called pOH, which is very similar.